Hello, everybody. Thank you for joining us today. This webcast is powered by Yole Développement and System Plus Consulting. It is entitled, How Are EV/HEV Trends Paving the Way for Power Electronics? My name is David Jordan. I'm Global Sales Support and Coordination Manager for Yole Développement. So before we start this webcast, let me give you some basic information on this online event. First, you will have the possibility to submit questions during all the webcasts. You can use the Ask a Question window at the bottom of the screen. We will answer as many questions today as we can, and for the remaining ones, we will usually follow up with you via email. Concerning the materials presented, please note that these presentations are already available, and you can download them from the resources section of the platform. Furthermore, tomorrow you will receive an email with the link to the recorded webcast session. So, let's start the webcast, and I am pleased to welcome Milan Rosina, Principal Analyst, Power Electronics and Batteries at Yole Développement, as well as Elena Barbarini, Semiconductor Devices Department Director at System Plus Consulting. The floor is yours.
Thank you. So, hello, everybody. Today we will talk about mainly the EV/HEV trends and how they will have an impact on the new electric cars. So in our presentation, we will have the presentation will be made by Milan Rosina and myself, and we will share the presentation. So there will be a switch in the presenters during all the presentation. So concerning the outlines of our presentation, at the beginning we will make a short introduction of the Yole Group and our activity. Then we will focus on the market drivers of the EV/HEV and the market forecast made by Yole Développement. In the second part of our presentation, we will present you the EV/HEV technology trends, and in particular, we will focus on the two levels, the vehicles and systems level. And then, since it's really connected to this part, we will focus on power module packaging level. And we will show there some physical examples. At the end, we will summarize our presentation with some takeaways. And finally, we present some related reports that we made on this subject. So let's start with a small Yole Group presentation. So Yole Group it's composed of different companies, and it's composed of more than 100 collaborators in different countries. The headquarters it's in Lyon, France, but we have collaborators all around the world, in Asia and in the USA. Our main activities are technology, market, and cost analysis. As I said, the Yole Group is composed by different companies, but this presentation will be made by Yole Développement and the System Plus Consulting, so two companies of the group. So Milan Rosina, it's part of Yole Développement company. Yole Développement focused on market technology and strategy consulting, evaluation of companies, and allows also direct access to the analysts for market research. System Plus Consulting is a sister company. I'm part of it, and we offer solutions and analysis on technology and cost analysis of electronic devices. We propose tear-down, reverse engineering, and cost simulation analysis and tools. Our business model it's composed of different offers. Here you can see all what we can propose to you. We offer standard report that you can find on our website. We propose monitors that are quarterly update report on specific subject, specific teardown tracks also online available, and then we offer also custom analysis tools and training methods on cost. So now I will pass over my colleague Milan that he will introduce you the market part of this presentation. So Milan, the floor is yours.
Thank you, Elena. Good morning, good afternoon, everybody. So my name is Milan Rosina. I'm from Yole Développement, and I will continue our webcast with the part about the EV/HEV market drivers and market forecast. So first, let's talk about the main drivers. So our society is see the different macro changes like population growth, increasing number of population living in cities. We see that increased CO2 emissions, so we would like to reduce, and limited resources, especially fossil fuels. So our society and industry has to adapt by offering the product and the solutions to produce more energy, especially clean energy, reduce the energy consumption, reduce the air pollution, especially in cities, and reduce CO2 emissions. This is what we need. This is what is the application pool. But if we talk now about the enablers, one of the enablers is actually the battery, especially lithium-ion battery, which is a high-efficiency, high-performance battery with high energy density. It's revolutioned currently the society and the industry, and on the different levels. So here are a few examples. In energy generation, we are going from fossil energy generation like coal and gas to renewable energy sources like PV and wind. But these are the intermittent energy generation. So without having the battery storage or the storage capability, it would be very difficult to integrate a high amount of intermittent electricity with the grid. So we need lithium-ion batteries there. And the clean energy could be used to power clean electric vehicles. So it is really strongly connected with electric mobility. If you look now on the electric mobility, we see that from the mechanical power, like e-scooter or the bikes, or the thermal engines, we are going to more and more electrically powered devices with electric motors. And actually, electric motors takes the energy from the batteries. So again, we find the lithium-ion batteries here. And if you look on the different devices, mainly in the past, mainly powered by cables, by electrical cables, these electric devices are more and more used or designed and built as a cordless devices. And of course, the lithium-ion batteries, high energy density lithium-ion batteries, enable completely new range of different applications like drones, watches, and so on, smartwatches. So we see that really the battery are changing our world. We go now, we focus on the electric mobility, and we go to the main driver. The main driver is actually today to reduce the CO2 emissions from passenger vehicles. So different regions of the world, different governments have set up targets to reduce the CO2 emissions. And the CO2 emissions here, the numbers shown here, are related to vehicle fleet average CO2 emissions in gram of CO2 per kilometer. So just to have in mind, it's about 195, 100, 110, something like this in the coming years. This is useful to better understand the following slides. If you look how we could decrease the CO2 emissions, it's actually somehow related, more or less directly related to the fuel consumption. To reduce fuel consumption, of course, we could have better motors we could reduce the consumption of different electric devices in the vehicle that take energy from the fuel. We could have different driving modes and improve the vehicle design, the chassis, etc. But this is not enough. This helps to reduce a little bit, but we need more. We need more, and how to do it? We need electrification. So with different type of electrification, from mild hybrid electric vehicles to full electric vehicles, but not only to electrified vehicles, but also to improve the devices. So it's not only to have full electric vehicles that generate zero CO2 emissions, but also to have very efficient electrical devices and electrical conversion in those vehicles in order to reduce the consumption of electricity for those vehicles. In such a way, we reduce the needs for energy generation for those vehicles. So this is also very important, not only to make electrified vehicles, but also to make highly efficient electrified vehicles. And here we'll look on the overview of different vehicles. So on the x-axis, we have the level of electrification. On the y-axis, we have the CO2 emissions. So as a reference, we take the thermal vehicles, 100% emission, so this thermal or internal combustion engine vehicle. And then we would like to go to something, a product that generates zero CO2 emission. And the examples here are battery electric vehicle and fuel cell electric vehicle. So one is battery powered, and the second one, the hydrogen, is first converted to electricity, and then electricity is used to power the car. So the transition from thermal electric vehicle to zero emission electric vehicle could not be done overnight. So we consider that there will be a kind of transition period, and during the transition period, different levels of hybridization will exist, from mild hybrid to full hybrid and to plug-in hybrid electric vehicles. And if you see, if we go in this direction, we reduce the CO2 emissions. This is what the automotive makers need, because they need to avoid paying the heavy penalties for CO2 emissions if they do not reach the CO2 targets set up by governments. So they need low emission vehicles in their fleet to reduce the fleet average emissions. And if you look on the values here, actually mild hybrid and full hybrid enable some reduction of the CO2 emission, but a significant reduction of CO2 emissions starts with plug-in hybrid electric vehicles, and of course the full electric vehicles and the hydrogen electric vehicles, it is the zero emission. So what is important here? Such significant CO2 emission reduction is important for the OEMs, so they need it, they want it. And if you look on this arrow here, that's indicated in this direction, we increase the power and also the higher battery voltage. So if we go this direction, we will have more power electronic systems per vehicle, and we will have higher power per vehicle. It means we will have more business opportunity for power electronic players. And this is also why many power electronic players are focusing on those two or three categories of, let's say two, because fuel cell, it's a very, very tiny market today. So there are many focusing on those two categories of vehicles. As I mentioned, we could not do this transition to full electric vehicles overnight. But what is important to say that this transition, if you look from the ICE to full electric vehicles, it was planned in the past that it will take some time. Of course, it will be done, but it will take some time, and it will be not so soon. And actually, what we've seen that have been different events that passed in the last month or years that have accelerated this transition. So in time, this transition will be done faster. And we show the increase of full electric vehicles or the plug-in hybrid electric vehicles much, much faster than expected a few years ago. And we expect that this transition will be also shorter. And what are the different factors here? So I provide a more or less exhaustive list here, but of course there are some others. For example, here the Tesla effect that reveal enormous interest in full electric vehicles. The incentive for zero-emission vehicles in China, which is the biggest market for the electric vehicles. Now it's a little bit changing, but it was a big boost in the past. Strong battery cost reduction. It was considered about 7% per year, but we have seen almost 16% per year. So this is something which really accelerated the transition, as the battery is the most expensive part of electric vehicle. So if the most expensive part of the vehicle is going significantly cheaper, then all our strategies we have to rethink, because this transition to full electric vehicles will be faster. And of course, we have seen the strengthening CO2 reduction target in Europe. We have seen the implementation of new norm, worldwide harmonized light-duty vehicle test procedure, which is more relevant for real life, real operation conditions of electric vehicle. And this is actually showing higher CO2 emissions compared to NEDC. It means for the same car, if we use the new norm, we have more difficulties to reach the target. More difficulties, it means we have to go faster, stronger, full electric vehicles. And of course, there is the impact of COVID-19 pandemic. So at short term, we see the decrease of the sales in generally for the automotive industry, and many other industries are also being impacted. But we consider that the crisis, it's also time to change, time to restructuralize the companies, time to change the strategies of the companies, and also time to use the post-crisis incentive financial packages to invest, to build the manufacturing facilities for full electric battery vehicles. So in the long term, we consider that there will be a positive impact. Even in 2020, we see that there is a decrease of the sales of automotive with cars, and many car makers are suffering actually. So here we provide you a short overview actually of our understanding how the market will evolve in the future. I think I hope I was clear enough to make you understand that we strongly believe in a strong increase of full battery electric vehicles here in green, and plug-in hybrid electric vehicles here in yellow. So from the about 5 million electrified vehicles in 2019, we consider we will reach the level above 30 million of electrified vehicles by 2025. And more than half of it will be full electric vehicles or plug-in hybrid electric vehicles. What is the advantage of plug-in hybrid vehicles? Why we believe in plug-in hybrid electric vehicles? Because this is not zero emission vehicle, but we have seen in the previous slides that the CO2 reduction is very significant. And also what is very important, that in plug-in hybrid electric vehicle, we have both thermal engine and electric engine. It means that we could use these vehicles as a full electric vehicle for about 50 to 80 kilometers today, maybe 100 kilometers next year, because of small battery integrated in the vehicle. So the vehicle could be run as an electric vehicle for short distances, which are relatively long actually. And if you have some issues, some fear about the driving range, the capability to drive 200, 500, 600 kilometers, we could still use a kind of backup this thermal engine. So we could refuel in a few minutes the reservoir for fuel, and we could drive the car farther. So we are not dependent on the recharging of this small battery in plug-in hybrid electric vehicles. But of course, this combination, this vehicle, it's expensive, it's heavy, bulky, so it is let's say, destinated to some specific vehicles, mainly big luxury vehicles. And if you look on the car makers that are producing plug-in hybrid vehicles today, it is matching very, very well. And the users that are used to use very comfortable vehicles today and do not care about the driving distances, they will definitely continue to buy such kind of vehicles instead of switching to full electric vehicles. At least for the next few years, because the full electric vehicles need still to increase the driving range. We have seen a very nice announcement about the, let's say, expensive cars with the driving range more than 700 kilometers. So this is the future where we are going. Definitely, we are going there, but we are still in, on, let's say, affordable cars. We are still more in the range 250, 400 kilometers. So this is something that has to be improved to develop the market for battery electric vehicles further. So now I will go more into details to present you some technology trends as a kind of introduction for the physical examples that will be shown by Elena Barbarini after my few introductory slides. So what is important to understand that if we speak about the innovations in power electronics, especially in packaging, actually in the past it was driven by industrial application. Then the photovoltaics boom and wind energy boom came, and we have seen a lot of development in this area. But today is definitely automotive, especially EV, HEV, is driving the innovations in power electronic industry, especially in packaging. So the technology trends are very different on different levels. So we have the market requirements, let's say the drivers, and to reflect these drivers, we have to develop specific systems, and the specific systems had to have optimized solutions on the package device level. And of course, this packaging has also matched the die material. So in the past, silicon was used. But today, more and more devices are based on silicon carbide and gallium nitride on silicon, or gallium nitride on sapphire is also coming to this market. So it is very important to understand that the different trends here, like car sharing, could result in different requirements on the system level, on the technology, on the device level. For example, car sharing means that our car will be used very often, or should be available most of the time. So we could not allow for a long charging speed. This is not very welcome. So we would like to go to fast charging. We would like to go to other characteristics here. And you see that these changes could be done on the system level and then on the packaging level. Go then further. So if you look on the OEM point of view, automotive car makers, they're building and selling cars. So for them, it's not so important to say to the customer what is inside of the vehicle. This is important that they sell the features that are interesting for the vehicle maker, for the customer. So let's take an example of full electric vehicle. In full electric vehicle, we have the battery. Then we have the vehicle. We could consider this as a black box. And then we have the wheels that turn. Okay? And these vehicles, a customer would like to have long driving range. So how to do it? Where we have to invest in and bid out of the black box to provide to customer high added value, a long driving range. So we could, of course, increase the battery, but we could battery capacity, but we could also increase something else. And if you look what it could be, so there are some possibilities how we could improve the driving range. We would like to go to driving range about 700 kilometers, 600, 700 kilometers. So we could improve the battery, of course, but this is not power electronics. But actually the battery parameters strongly impact the power electronic behind. So we could use a high voltage battery or high voltage circuitry. So we speak about the 800 volt battery approach. We could use highly efficiency conversion to reduce the losses from the battery on the way from the battery to the electric motor. And of course, we could use highly efficient and lightweight motor to reduce the weight of the vehicle and to reduce the losses from the battery to the wheel. And of course, we have to reduce the auxiliary consumption because they are also using the energy from the battery. So if the auxiliary loads are high, we will have less energy going to the wheels because a bigger part we will go to the loads. So if you are speaking about LiDARs, about sensors, about entertainment and other applications in the vehicle, like heating, ventilation, and so on, this is also something what we have to look in detail. But today, I would like to attract your attention on this part, on the higher electric voltage circuitry, especially related to 800-volt batteries and to traction inverter. The traction inverter, this is a power electronic system. It is a high power and a high amount of power electronic devices and strong challenges on power electronic devices. So on this chart, I would like to show you the different car categories plotted in the function of battery pack voltage. So this is the big battery which is inside of the car, this specific voltage, and the electric motor power in the vehicle. So typically, this is a hybrid electric vehicle, plug-in hybrid vehicle. There are between 200 and 400 volts. And today, the full electric vehicles are typically about 400 volts. But there is a trend to go to so-called 800-volt battery approach. And this 800-volt battery, it could be the vehicles, let's say, from 650, which is the case for Concept 1 from Rimac, or C2, or until 900, which is today the Lucid Air car. But typically, we speak about the 800-volt approach to differentiate it from the conventional vehicles today. And this actually enables fast charging. This enables the reducing the losses. This enables to have smaller diameter cables in the vehicle. It means easier integration of these cables in the vehicle. So there is several advantages here. And what is important also that if we go from 400 volt to 800 volt battery, then the power devices that are used in the system, like traction inverter that is related to the battery, they also change the voltage range. So for 400 volt battery, typically we use 650, 700, 750 volt silicon IGBT or silicon carbide MOSFET in Tesla. But if we go to 800 volt, we have to switch to higher voltage level. But if we switch to higher voltage level, 1200 volt, what we'll find, 1200 volt is actually the voltage level, where silicon carbide MOSFET is very mature. You will find a mature device, very well developed, proposed by different suppliers. So you have a choice of supplier. You could better negotiate the price, and you have less supply problems. So this is kind of opening the opportunity window, additional opportunity window for silicon carbide. And if you look a little bit on the different approaches, 800 volt versus silicon carbide. So the different approaches for different companies, what we have seen today. Tesla, they kept the 400 volt battery, but they went directly to silicon carbide. Porsche Taycan, the first commercially available, large volume available vehicle, they went to 800 volt. They have excellent charging time, very short charging time for their vehicle. And the next step could be to adopt the silicon carbide in such vehicles to even improve the performance and improve the driving range. Toyota is doing a little bit different approach. They have a low voltage battery, but they use so-called boost converter to increase the low voltage from the battery to higher voltage circuitry. And the inverter then, after a boost converter, is designed for higher voltage level. So here, if we are also at higher voltage level already, so the next step could be pretty logical to go to silicon carbide. And actually, Toyota is very well known to thinking or to developing silicon carbide since many years already. Okay, so now we go to trends to power module packaging. So I will go a little bit faster. Why power module? Because power module is a key element of power electronic systems. This is the let's say the key brick onboard charger or high power onboard charger or traction inverter or boost converter. It's the power module. And the power modules actually today is produced by power module manufacturers, but in the future, we see that there is more and more players from the supply chain, automotive supply chain. They are coming to, they are intrusive in this area. So we see the tier ones like Bosch or the others. They are already manufacturing the power modules, but for automotive industry, but also automotive OEMs. They are developing the specific designs, and in the future they may become very intrusive also in manufacturing of power modules. And this is very important to understand because the power modules in tier one and automotive do not have the same strategy in developing, in design, and in selling the power modules. So if you look on the different characteristics for the packaging solution, we have the application requirements, system characteristic. They are different for onboard charger, for traction inverter, and so on. And of course, if we use silicon carbide, we have different requirements. Then for the dies, they are based on silicon or gallium nitride. And of course, the cost is important here. But the application requirement, this is mainly the business about the OEMs. They know very well how the vehicle will be used. Systems, it's OEM and tier ones. And power module manufacturers, they are very well know how to match the die properties with the packaging requirements and to answer the expectation of both tier ones and OEMs. So we have actually the different needs. They are reflected in different needs on the electronics and the needs on the packaged devices. So we need typically the devices with better reliability under thermal cycling. This is very specific for electric and hybrid electric vehicles. Low inductance to get a shorter interconnection or specific interconnection, electrical interconnection to reduce the inductance, to reduce the losses, enable faster switching at higher frequencies, to enable higher operating temperature, and to dissipate the temperature from the die much easier, much more efficiently to the heatsink. And you could find the different solutions on the base plate level, on the module design level, on the die attach level, or replacement of aluminum wire by copper wire, or by ribbons, or by copper clips, different types of cooling designs. So there are many different packaging solutions that exist and they are being developed. What is important that the package has to match the requirements of the die, as I mentioned, from the system, from the application, but also on the manufacturing. So we have to keep in mind so-called design for manufacturing. The package must be not only efficient, but also cheap and reliable to produce with very high yield, with high throughput, and if possible, with available equipment already. And so if you build something very highly optimized here, we will probably find something very different from the standardized product. But the standardized product enables the reduced manufacturing cost. And therefore, there is a kind of battle reflection. What is better, to a highly customized product or a highly standardized product? Actually, the answer is not easy, because the power module makers, they would like to have proprietary design to differentiate, to show we have better product than our competitors, buy from us. Automotive makers would like to have something more standardized. As we see it in a real market, that the standardization is coming already in power module business, but very, very slowly, and it's far away to be implanted or adopted in EV/HEV. So in each EV/HEV, we have today we are more in proprietary design. Highly standardized will be nice to have reduced the cost, but today more proprietary design are used. So Elena will show in a few minutes the different examples of proprietary design for different devices. What is important to mention, if automotive OEMs go to power module manufacturing, they will become module makers, and they will probably also be interested in proprietary design. So this is very important to understand the notion whether they need proprietary or highly standardized it's also depending on what is their position today and what will be their position in the future. What we consider that actually we could go from something highly optimized, big power modules, which have a lot of proprietary solution in it, and we've compared it with discrete power devices, which is pretty standardized packaging, especially TO, but also the others. They are produced by many players in very high quantities at a low cost. We could consider that in the future there will be a trend to go to so-called in-between solution, or we called it discrete-like power modules. What does it mean? It means fewer chips per module, so fewer dies. So we will have 2-in-1 module, for example, and typically slim card-like design. And this will provide the benefits as lower entry barrier for newcomers for power devices. So this is for the newcomers in EV HEV, or the companies that are already in EV HEV, but the newcomers in power module manufacturing. And this is also opened a business opportunity window for discrete packaging players that could develop their business, enlarge their business from discrete devices to something like discrete-like devices. So in this stage, I will pass you over to my colleague, Elena, and she will show you some examples of real product.
Thank you, Milan. So to understand which will be the future trends in power modules device for inverters, let's first have a look about what happened in the past years. What's important to see is that actually the design itself of the inverter has changed in the last years. Let's say that in the past, the motor inverter, the generation inverter, and the boost converter were all designed in one block with one cooling system. In the latest year, we have seen the trend to go to a smaller module, as Milan already introduced in the previous slide. So smaller modules, more compact, but also smaller commutation cells in the module itself. So here you have a short storyline of the evolution of modules. At the beginning, in the Toyota Prius, we have all the three parts of the inverter on one single surface with one cooling system. Then with the integration of 6 in one commutation cells from industry to automotive, we see the modules proposed, for example, like the hybrid pack drive proposed by Infineon. And then the introduction of molded modules and the double-side cooling modules. So if we have, as Milan introduced, we need to understand which is the application, which is the type of system design of the car, the level of electrification, and also the power of the modules to understand which is the design of the modules itself. Because obviously, if we change the level of electrification and the power, we need a different thermal management in the module itself. So what we have seen is that there is a trend toward the overmolded double-side cooling modules and thin-fin modules. An important aspect to take account, it's obviously the cost of the modules. And so actually the design has an impact on the cost. So let's have a look at some example of these modules. As I present you in the timeline, one of the first modules that we have seen on the market was the Viper, or Cool Air module designed by International Rectifier. So this is a really interesting modules because it has it's a one-on-one commutation cells module. So every module represents one commutation cell. It's double-side cooled modules with aluminum nitride ceramic substrate. So every module has one IGBT and one diode. And in this module, it's really interesting the interconnection that actually are made with flexibles and not with copper clips or wires. So this is one of the first example of single, let's say, device like power modules, and that it's still used integrated in electric cars. The second example of single modules for electric cars is the Mitsubishi modules for Honda. In this case, here you see the introduction of molding. So the introduction of a molded module with a copper clips, more than the wires for the gate of the transistors. And it's interesting here, the introduction of EMS has a substrate. So this is a module molded but with single side cooling system. And we see also here the introduction of EMS that allows a better flexibility in the manufacturing itself of the modules and the design. A third example of modules is the Toyota Prius. So as you have shown you in the timeline, Toyota for the first Prius proposed all-in-one system, and then with the Prius 4 changed completely the design. The advantage of Toyota to do that is actually they control the complete supply chain. So actually they work in collaboration with the manufacturer of the die and the module itself, so they can adapt the design of the modules to the design of the inverters and finally in the design of the car. So the Toyota Prius is one of the first that proposed a double-side molded module with the copper substrate for the thermal dissipation. And it's interesting here to see that actually the isolation, it's not inside the module, like, for example, the Viper, but you will find the isolation in the system itself and on the cooling system. Our more recent example of double-side cooling molded modules is the Infineon hybrid pack. Infineon entered in 2017 with this type of modules and proposed a different design actually of this type of modules, so with 2-in-1 or 4-in-1 commutation cells according to the need of the customer. And here you see actually that the isolation, it's integrated in the module itself. That's allowed a bit more flexibility in terms of design of the system. So the problem of isolation is included, it's solved inside the modules. So the last example of discrete power module is the module of ST for Tesla module. So obviously in this case we have the integration of silicon carbide die. The previous example that I show you are all with silicon IGBT. In this case we have the introduction of silicon carbide. So the design of the module has been completely reviewed. The module is a single side cooled. Is overmolded with copper clips. And so also here you see the substrate has been changed according actually to the use of the silicon carbide MOSFET. I want to highlight the cost in this type of modules because we have seen that in the power modules up to now, in the power modules for cars, for electric vehicles, the main cost drivers are actually the materials that are integrated in the modules itself, so actually the packaging. So that's why our presentation also will focus on these thematics, because the silicon itself is no more the cost driver, but actually the design, the manufacturing of the modules and the materials used in the modules. Obviously, when we pass to the use of silicon carbide MOSFET, the die itself becomes again a cost driver. It's interesting to know that this type of design actually was optimized for the silicon carbide MOSFET, but then the same discrete-like design of modules has been done also with silicon IGBT. So let's say that silicon IGBT are still present in electric cars, and they will be still competitors for silicon carbide MOSFET, at least for some applications, some integration in the modules. The second type of modules that we have seen, the second type of trend, it's the use of direct cooled technology. So the first example that I show you are modules where the cooling system actually is not inside the modules, but it's the module itself, and then the cooling system should be integrated by the designer of the inverter. And then we have a second generation of power modules where the cooling system is directly integrated in the module, so with the use of thin base plate. This is a solution that is really appealing for the manufacturer of the modules, but also mainly for the integrators. So in that case, the integrated pin fins allows the minimization of the stacking layers and removal of the thermal interface stress materials, and then a direct contact of the modules with the dissipation liquid. So as an example, the first example is the Infineon hybrid pack drive. So the first presented on the market. So here is a 16-1 module from Infineon. So the concept has of cost. Again, I want to highlight here the concept of cost, since the silicon IGBT here with a standard technology. So the main impact in this kind of modules, the main cost trends are the assembling and the use of the materials for the packaging. As these modules, it's one of the first, but it's still used in automotive solution. A second type of module is the Mitsubishi J1. So Mitsubishi proposed also the integration of the thin film for industrial and automotive application. So the type of design of modules, you can find different types of design, integration of commutation cells in this type of modules. But here it's interesting the use of molding, actually, that we have seen in the previous modules, and the integration of heat sink, of a pin fin in heat sink in the module itself. A third example, the last one, is the Hitachi. So Hitachi, thanks to the strict collaboration with Audi for the design of these modules, so actually for the strict collaboration with the designer of the inverter and the car, propose a really specific module. So a module that is double-side cooled. It's molded inside because of the card itself. Actually, it's molded before to be integrated in the heat sink system. and it has PinFin included. He has like all the modules with PinFin integrated, an insulating layer already integrated in the modules. So if we summarize which are the solution and the trends that we have seen in the latest years, and we will expect that will be in the future, the next years, here you can find a summary of the trends. The design of the standard modules that come from industry is slowly redesigned and changed according to the need of automotive industry. So we've seen the integration of more and more copper lead frames for the interconnection, the use of molding not only for the double-side cooling but also integrated substrate, and the use of different type of soldering. So as Milan introduced, the design it's okay, but every time we change the design, we need to think about the cost impact that the design can have on the final module. So if we have a look, a small analysis of the different costs of the modules, we have seen that we can show you that actually the cost it's as a parameters, and actually has to be shown. The design of the module has choose according to the integration that you want to put in your car, and adapted to the power request, the integration in the inverter. It's logic that if you make a comparison of the cost of the commutation cells, if you if you add the heat sink in the module itself, the cost of the commutation cells will be higher, but then you will save cost in the design of the system itself. And last point, with the integration of the new materials, so the change of the type of die, and now up to now silicon carbide, but why not gallium nitride in the future? You will have different costs driven by this die, but that will probably help in the optimization of your final power modules and then final system. So that's what all for me. I will pass back the word to Milan to make a takeaway of our presentation. So Milan, the floor is yours.
Thank you, Elena. So I would like just to summarize and to be the key messages from today's webcast. So EV/HEV application, it's definitely the main driving force for innovations in power electronics in general, but specifically for power module packaging. The main needs are increasing reliability, better efficiency, higher power density, but of course we need also the cost reduction. And with the maturing EV/HEV market, the cost reduction issue or the importance of cost for manufacturing will be growing. So this is something absolutely to keep in mind. The best efficiency solution, it's not the solution that will match all requirements of the OEMs, especially for mass-produced battery electric vehicles. Power module packaging market will be driven mainly by PHEV and BEV. This is because we have the strongly growing market and high volume market here. This is actually the almost ultimate goal of the electrification of the vehicle fleet. So we're strongly convinced that most or a majority of the power module makers are focusing on those on the developing of the innovative solution for those applications. Regarding the packaging, the alternative interconnections with lower inductance and a greater reliability, this is something which is important, and this is really these solutions are gaining the market share. we see the arrival of copper clip solutions that have been typically used in discrete devices. Now we see them also in power modules. In encapsulation, we see still both silicon gel and overmolded or epoxy-based modules, but the trends are definitely towards overmolded modules. Even if they struggle a little bit from the operation at high temperature, but several players are developing the epoxy for high temperature, so this should be not the big issue in the future. Silver sintering is definitely the technology that has made a great appeal for the die attach in EV HEV power modules, but not only for die attach. In silicon carbide inverter in Tesla, we have seen that the applications of silver sintering are beyond die attach. It could be also to use to attach of the power modules. It could be used to the attach of the base plate in some cases. So silver sintering definitely will play a very important role in EV HEV power module packaging. Regarding the ceramic substrates, they are used for the insulator electrical connections in the power modules. The most cost-effective solution is aluminum oxide, but the trends are toward the material with higher thermal conductivity, like aluminum nitride and silicon nitride, especially for silicon nitride A and B, because this is very good mechanical properties, thermomechanical properties during the thermal cycling. Double-side cooling is something definitely what we see to grow, but still we see that the single-side cooled power module are preferred by many players, and the structured baseplate by like pin-fin or the ribbon baseplate or the specific proprietary solutions like power shower power from Danfoss and the others, they are gaining interest for direct cooling in automotive industry because we have the liquid cooling available in the car. And the baseplate free modules are increasing their market share because the increase of double-side cooling modules and the trends to a reduction of the thermal interfaces. If we reduce the number of thermal interfaces, we could get a better thermal dissipation. So I would like to thank you for your attention. Here are just some examples of the Yole Development Technology and Market reports, where you could find more details about the topics we have discussed today. And I would like to thank you for your attention. And we will be glad to answer your question if you have maybe still few minutes time.
Thank you very much, Milan. Thank you very much, Elena, for your relevant presentation. We are now going to wrap up the webcast with the Q&A session. We are unfortunately a bit late, so we'll answer only one question for each of you. So for the remaining question, we will answer by email. Don't worry. The first question for you, Milan. What will be the winning approach, double-side or single-side cooled module designs?
Yeah, this is a great question. Actually, both designs of both approaches have the supporters and the power module makers and also the integrators. We consider definitely that the double-side cooling approach is something which is definitely growing because we need much better heat dissipation from the die. And actually double-side cooling, especially cooling from the top side of the die, is increasingly growing in importance. And once we get rid of wire bonding and we implement a new electrical interconnection solutions, it will be a little bit easier to go with double-side cooling. But single-side cooling is definitely something we will also keep on, and we see it in many innovative approaches today.
Thank you very much, Milan. So one question and last question for Elena. Why single-side cooled modules are still preferred by many players?
Okay, so actually, in terms of assembling of single-side cooling modules, the assembling it's much more easy and cost effective. So that's there's more preference for this type of modules for a cost point of view and assembly point of view, both from the side of the designer of the modules because of the manufacturing line, and for the system integrator also. The single side cooling modules, it's a bit more easier to integrate, actually to have a better uniformity of cooling. The double side cooling modules, it has to be taken account the perfect uniformity of the cooling systems on both sides of the systems, and so implies also a reflection of the cooling system of the system itself, actually the inverter itself.
Thank you very much. So the webcast is now over. You will soon receive an email with the link to the recorded session. And also feel free to share this presentation with colleagues. And also let me remind you that you can find all our products on our website, i-micronews.com. So market reports, teardown, and also tracks and monitors. Do not hesitate to contact us if you have additional questions. You can find our contact details on the last slide of the presentation. Thank you very much for joining us today. Have a very nice day. Goodbye.